So, welcome to our group talking about adaptive cruise control by Group 12. So, here we have our group members Christy, Zi Jian, Hai Yang, Jin Young, and lastly, me, Royston. So, now here is the content of these following slides. For example, the requirements, flowchart, and block diagram.
The journey of cruise control began in the 1950s, offering drivers a way to maintain a constant speed. With the advancement of sensor technologies in 1990s, adaptive cruise control was born, initially featured in luxury vehicles, and now is accessible in many car models. Adaptive cruise control employs a combination of radar, lidar, and camera systems to continuously monitor the road. It calculates the distance and speed of vehicles in the same lane, automatically adjusting the throttle and brakes to maintain a safe and comfortable driving experience.
So, what are the requirements of an adaptive cruise control system? One of its main components include the radar, and it is defined as an electromagnetic sensor used for the detection, the location, the tracking, and the recognition of obstacles at a distance. It works by transmitting electromagnetic waves at objects, then receiving the echoes produced to analyze the object distance via the measurement of the time taken for the signal to make the round trip to the obstacle and back from the obstacle. From the measurement of the distance of the obstacles, their velocity, their location, and their angular direction can also be found. It can also detect the shape and size of the obstacles. Radar usually operates at a frequency of 400 MHz to 40 GHz, with some radar systems going as low as several megahertz for long-range applications. The transmitter and the receiver are attached together on the antenna, which is shown in the figure to the right here. The size of radar systems can vary from handheld to needing big pieces of land to work. Another component that is essential in adaptive cruise control systems is the controller, and its function is to read the signal or the speed of the obstacle approaching the car from the comparator, which is the radar sensor, in this case, to produce another unique signal meant to control the actuator or the brakes, in this case, in the desired way. Controllers are usually made out of microcontrollers due to the fact that they provide control functions in a very compact manner, and that microcontrollers also provide the benefit of high levels of flexibility since they possess multiple pins for the connections to multiple input-output devices. The figure to the left here shows a microcontroller. The next essential component in adaptive cruise control systems is the actuator. In adaptive cruise control systems, there are two types of actuators, with one being used to slow the car down and one being used to accelerate the car. When the actuator is used to slow the car down, the actuator is the brake system, and it reads the signal from the controller to slow the car down in the desired manner so as to avoid collision with the obstacle approaching the car. And the brake caliper is used to make this work. The top left figure shows a brake caliper. When it comes to accelerating the car, the actuator is the throttle input, and it is controlled automatically by the adaptive cruise control system, beginning with reading the signal from the controller under the conditions of having no obstacles in close proximity, then putting more input into the throttle to pick up speed. The bottom left figure shows the total body of a car. The last important component in the adaptive cruise control system is the display. And the display in adaptive cruise control systems is the brake indicator lights behind cars, as shown in this figure below. The signal from the activation of the brakes or the actuator will light up the brake indicator lights, and the activation of the brakes happen when an obstacle gets too close to the car.
The flowchart here shows the overall system of the adaptive cruise control system. To begin with, the system will firstly start its function followed up by a checking algorithm. The system will check if the ACC system has been turned on or off by the driver or not. If no input has been detected, the system will then continue monitoring the system and repeat its function to check the inputs from the driver. If the input is detected by the system, it will then process the data retrieved from the sensors and then control the speed set by the driver while monitoring and adjusting based on the surroundings. After that, the system will check the inputs from the driver to deactivate the ACC system. If no input is detected, the system will continue to monitor and adjust the vehicle. If an input is detected, The system will return the controls to the driver and end the ACC system, which will restart again from the start.
For the block diagram, we can split up the diagram into two different systems that functions under different circumstances. The first block diagram represents the system that is active when an obstacle is detected. The radar sensor on the vehicle would send the detected signal to the controller, and once the controller receives the signal, it will perform two tasks. The first task is to send commands to the brake actuator to stop the vehicle, and the brake actuator will signal the brake input to activate brake system. At the same time, the brake actuator will signal to turn on the brake indicator. The second task is to send command to the speed actuator to stop throttle system. The speed actuator will then signal the throttle input to gradually reduce the vehicle speed until the throttle is completely stopped. The second block diagram represents the system that is active when no obstacle is detected and the vehicle is in motion. Similar to the previous system, the controller will perform two tasks once it is confirmed that there are no obstacles and the vehicle is in motion. The first task is to send command to the brake actuator to release brake. The brake actuator will send signal to the brake input to release the brake, and at the same time, it will signal the brake indicator to turn off. The second task is to send signal to the speed actuator to accelerate the vehicle to a specified speed. The speed actuator will convert the signal into commands to the throttle input to gradually activate the throttle system and increase the vehicle speed.
How does the ACC control system function? It functions in a way where it controls the accelerator and brakes to maintain a predetermined distance by automatically altering the speed of the automobile to match the pace of the car ahead. The ACC control system uses a variety of sensors such as a distance sensor and a speed sensor, which automatically accelerates or decelerates the vehicle. We can see the activation and deactivation of the ACC system. The ACC system can be located on the steering wheel of the car, which has the green, interval, and the up and down switch of the positive negative value, which can adjust the speed accordingly to what the user desires. In the green part is the desired speed that has been set by the user, the interval speed, which is the speed that the car is currently traveling. Now we move on to the ACC function diagram. Here we can see there are two cars, which is the Eagle and the lead car, at a relatively safe distance. But when ACC has been set in, the Eagle car will move to the safe distance of the lead car. For instance, if the driver sets at the speed to 75 and the front car is at 60, the ACC will modulate the accelerator and the brakes to ensure there's a safe distance between the two cars regardless of what speed has been set. And within the ACC control system, there is a radar that emits radio waves, which calculates how long it takes to return to the ACC sensor and analyzes the distance between the two vehicles. A radio wave is important because it is able to detect the car in front and maintain a certain safe speed to ensure that there are no collision caused when ACC has been set to follow a certain speed. Diagram above, here we can actually see the block diagram of the ACC system in a more simplified version. In the control loop, there is a controller, a throttle unit, an engine, and a gearbox, and in the feedback loop there is a speed sensor. So, the purpose of the controller is to send signals to reduce the deviation of the actual value from the desired value to almost zero or lowest possible value. It means that the controller will compare the actual values and the derived value that has been calculated by the ACC control system. Followingly, we have the throttle unit, which tells the system to whether to accelerate or decelerate the car based on the calculated desired value by the controller. Once that has been calculated and the throttle has decided it wants to accelerate or decelerate, it moves on to the engine and the gearbox. The engine will power the throttle system and increase the speed or decrease the speed of the vehicle. However, if the user has set the desired speed to a much lower value, it will feed back to the speed sensor, in which the speed sensor will determine the speed that the car is going and send this back to the error as an error back to the controller in a single controlled loop.
The design of a predictive adaptive cruise control system involves addressing several critical challenges to ensure its effectiveness and reliability. The first challenge is latency in response time. Delays in processing signals can significantly impact the system's ability to react promptly, especially in high-speed scenarios. To mitigate this, it is essential to implement faster processors, utilize real-time operating systems, and optimize communication protocols to reduce latency. Another major challenge is sensor accuracy and reliability. Adverse weather conditions, such as fog or heavy rain, can compromise the performance of the radar sensor. To address this issue, employing redundant sensors, such as combining radar with LiDAR and cameras, can enhance reliability. Additionally, implementing sensor fusion algorithms can improve the overall accuracy of obstacle detection. Actuator reliability is also crucial, as any failure in the brake or speed actuators can lead to serious accidents. Ensuring the use of high quality, fail-safe actuators is necessary. Regular maintenance and diagnostics should be conducted to verify the proper functioning of these components, thereby enhancing their reliability. The complexity of controller algorithm poses another challenge. Efficiently processing multiple inputs and outputs can be complicated and prone to errors. To overcome this, developing robust control algorithms with fail-safe and redundancy is crucial. Extensive simulation and testing under various scenarios can help validate these algorithms, ensuring their robustness. Apart from that, communication failures between system components can disrupt functionality. To address this, robust communication protocols with error checking and correction mechanisms should be implemented. Additionally, using redundant communication paths can maintain system integrity even if one path is failed. Finally, power management is a significant challenge. The radar sensor and actuators require substantial power, which can drain the vehicle's battery. Optimizing power consumption of these components and employing efficiency power management systems are essential to ensure the vehicle's power supply can support the additional load without compromising performance. By addressing these challenges with the proposed solution, the predictive adaptive cruise control system can be made more reliable and effective, ensuring better safety and performance in real-world driving conditions.
And that's it. We have covered the definition of adaptive cruise control systems, the requirements of adaptive cruise control systems, in this case being the radar-based adaptive cruise control system. We've covered its flowcharts, its block diagrams, how it works in general, and the potential problems associated with its operation. Thank you for watching this video.